is John, a young, not-so-experienced structural engineer. Day after day, he poured his energy into drafting blueprints, chasing perfection in every line. And finally, his first creation stood tall. But nature is a force that cares little for ambition. The bridge sways, then collapses into the rushing waters below. In the aftermath, blame came swiftly. Mockery followed. By the time he returned home, the weight of failure pressed heavily upon him. Even the news was relentless in reminding him. Frustration, exhaustion, and the creeping thought of giving up. But then, something strange. John awoke to find himself face to face with a bee. No, not just meeting a bee, becoming one. Panically, John weaves through the forest, heart racing. He lands by a shimmering pond, wings trembling. His gaze sinks into the still water below. Bubbles form, revealing a bee staring back. Suddenly, John jolts awake.
What?
He staggers to the kitchen, weary and tense. Mid-sip, a spark of realization strikes. Suddenly, it hits him. Perhaps the answer lies behind Hexagon's ability to form regular tessellations. John runs a simulation for the hexagon. Under load, the hexagon deforms, unable to hold its own shape. To determine why, John uses a simple but essential equation, the planar truss determinacy equation, which allows John to determine whether or not a structure is statically determinate, therefore determine its stability. By implementing the equation, John realized the hexagon is indeed not statically determinate, therefore making it unstable. However, the ability to form regular tessellations would prove useful in creating a support structure due to its material efficiency. It turns out bees don't use hexagons for structural stability. They use them because hexagons pack space efficiently and fit together without gaps. Upon further research, John discovered squares and triangles also possess the ability to form regular tessellations. Therefore, the testing begins. First, by using the equation, John finds out that a square isn't statically determinate, making it unstable and unsuitable for his project. Further simulation proves square is indeed unstable by itself. Finally, calculation for a triangle shows that it is statically determinate, providing it the stability to hold its own shape. Further simulation proves a triangle is capable of maintaining a rigid and stable body despite the lack of bracings. Last but not least, John has to accurately determine the forces acting on each joints and members of the truss. By applying Newton's third law, we are able to determine the reaction forces on each of the main support joints of the truss using the torque equation. Since we don't know which members are in tension or compression yet, let's assume that all members are in tension. Therefore, the internal forces will be drawn as pointed away from each joint. To calculate the forces acting at joint A, since the 10 kilonewton reaction force must be cancelled by the vertical component of force AB, we can calculate FAB as -10 divided by sine 60 degrees. Next, by using the equilibrium equation sum of Fx equals 0, we can determine the force AC as it must cancel out the horizontal force of AB. Since the forces in each member is constant, we can determine the forces acting on the joints at the other ends of these two members. We can repeat the process to determine the forces acted on joint B by considering equilibrium for vertical and horizontal forces. With that settled, we now need to determine the remaining forces acting on joints A, C, and E. Since the truss has an axis of symmetry, we can assume that the forces on both sides are identical. Therefore, we are able to obtain all the forces acting on the joints. Finally, notice how certain forces are in the negative values? This means that instead of being in tension, these truss members are actually in compression. Therefore, we are able to determine the forces that each of the members have to withstand, as well as determine which members are in tension and which are in compression, represented in blue and orange, respectively. This allows us to select the best cross-section for each members, thus maximizing material efficiency. Not only are triangle trusses rigid, they are also able to convert the bending moment acting on the bridges into tension and compression, which are capable of carrying significantly larger weight. Late at night, he stands by the window, deep in thought, imagining the bridge design taking shape in his mind. Slowly, his vision of the perfect bridge materializes through his computer. He presents the design with fierce pride. Tests prove it unshakable. Through resilience and his undying determination, his bridge stands strong, ready to bear the weight of thousands.
Ah, le tengo ni.